So now we are going to practice the stuff that we just talked about. We're going to do the first 4 problems on this worksheet. We're going to practice picking pairs of molecules to make a buffer. So the first question is asking you, if you had HCN, what could you combine with HCN to make a buffer? So the buffer needs to be an acid and its conjugate base, or a base and its conjugate acid. The thing that we are looking for when we're trying to find a partner for HCN, we are specifically looking for a common ion So we want to look for something that has either the hydrogen or the cyanide ion in it. And let's just kind of go through what we've got. KCl does not have common ion, so that's a definite no. The next one, HNO3, you do see the common hydrogen ion, but remember that strong acids are not allowed, so that guy gets crossed off right away because it's a strong acid. KCN looks good. It's not a strong acid or a strong base, and it has that common cyanide ion present. So yes, that looks great. Let's go with that. That is what we have. That's going to work. Maybe there's more options. NH3 has no common ions in it at all. So that is not an option. It is true that there are hydrogens there, but those are not H plus hydrogens. Those hydrogens are a part of the NH3 molecule. It does not dissociate any of those hydrogens off of it. So there's only one possible choice for this combination. Let's look at the next one. What could you combine with HNO3 to make a buffer? Well, this is actually a trick question. HNO3 is a strong acid, which means there's nothing that you could put together with it to make a buffer. It's just never going to work. So let's move on to the next couple of problems. The next couple of problems are asking us to calculate the pH of a buffer. Calculating the pH of a buffer. We've been doing nothing but calculating pHs for this whole entire quarter, and maybe you have a little bit of calculate the pH trauma because it almost always involves using an ice table, which people get really tired of using. But fortunately for buffers, if we're trying to calculate the pH, we don't need to use an ice table. We can use Henderson-Hasselbalch, which I'm just going to call HH because Henderson-Hasselbalch is a really big name. So we can use HH to calculate the pH of any buffer. And we should use this equation because it is way faster than making an ice table. Although we certainly could make an ice table if that's what we wanted to do. Look up the Henderson-Hasselbalch equation. You don't have to have it memorized. pH equals pKa plus the log of the concentration of the base over the concentration of the acid. And now we're just going to plug stuff in. The pKa is the negative log of the Ka, just like pH is the negative log of H3O plus, and pOH is negative log of the OH. So pKa is the negative log of Ka, and for this buffer, the Ka is 1.8 times 10 to the minus 5, so our pKa is 4.74. 4.74. And now we need to figure out what the concentration is of our base and what is the concentration of our acid. We're given 2 concentrations in this problem, and actually we're kind of in luck here because both the acid and the base have a concentration of 0.5. So we don't even need to think about which is which. We're going to get it right no matter what. But don't worry, I'm going to tell you how to figure out which is which. Let's just go ahead and do the math on this, and then let's talk about how we'll know which one is the acid and which one is the base. So the log of 1 is 0. which means that the pH of this solution is 4.74 plus, I'm going to write all the math out here, the log of 1, which is 4.74 plus 0, 4.74. The next problem that we're going to do is it's not going to be, we're going to have to know which is the acid and which is the base. And in general, you're going to have to know which is which. So let's write down the simplest way, the fastest way for you to tell the difference between the acid and the base. When you're looking at their formulas, the acid is going to have an extra hydrogen, has one more hydrogen than the base. That is going to be your fastest way to find which is the acid and which is the base. And if you look at these two, you'll see that it holds true. So the first one, CH3COOH, that has a total of 4 hydrogens, and the other CH3 has only 3 hydrogens. So the acid, CH3COOH, does have an extra hydrogen on it, so it holds true. There's a reason for that. There's a reason, it's not random. The acid is a hydrogen donor. So the acid has that extra hydrogen to donate. Let's try this again with the second problem. Calculate the pH of a buffer. So that means we're gonna use Henderson-Hasselbalch. pH equals pKa plus the log of the base concentration over the acid concentration. Ooh, look at this. We are given the pK, or the Kb, not the Ka. We totally have this though, no problem, no problem. So remember, so many of these relationships are the same. pKa plus pKb equals 14, just like pH plus pOH equals 14. So if we figure out what the pKb is, we'll be able to figure out what the pKa is. So that's going to be our strategy. The pKb is the negative log of the Kb, which is the negative log of 1.8 times 10 to the minus 5, which is exactly the same as the Ka in the problem that we did just now. So the pKb is going to be 4.74. pKa plus pKb is 14. So pKa is 14 minus the pKb, which is 14 minus 4.74, which is 4.74, 9.26. So our pKa is 9.26. We're ready to plug in the concentrations of the base and the acid. Let's look at our formulas. NH3 has 3 hydrogens. NH4Br has 4 hydrogens. The acid is the one that has the most hydrogens. NH3 is our base. 0.074 is our base concentration. Over 0.17, that's our acid concentration. Totally running out of room here. I'm going to mark this stuff off. And this, which is all part of this problem up here. And let's do the math on this. 0.074 divided by 0.17. Take the log of that and add 9.26, and we get a pH of, definitely did something wrong, minus 0.36, 8.9.